Welcome, everybody. Good evening. Usually you talk about being between you and the lunch. That joke is so much better than between lunch now and dinner. So we'll try to make it more fun as we go along. A little bit of trivia to get started. Chris and I go back a long way in Microsoft. The last time we were on stage together was 17 years ago. So it's like after 17 years, so we're excited that we're both here talking about some cool stuff with you guys. So in this session, we will talk about several things. The main thing here being, how do you use Azure ML, something that you've been using all along for doing some of the coolest stuff with Gen AI models. We'll talk about how do you basically take a multimodal model, fine-tune it, how do you take that, how do you take a base instruct model, create a reasoning model out of that, put that together in an agent, and solve some really cool problems. So that's what we're going to do. And we'll get started with Chris. Chris, take it away.
Thanks so much, Vijay. And thank you all for joining us this evening. I feel incredibly lucky to work at Microsoft with amazing people like Vijay and so many others. But one of the things that I love the most is that AI isn't just hype here. We're using AI to transform the world, make it a better place every single day. And one of the exciting applications that we've built at Microsoft that is the inspiration for today's demos and talk track is Dragon Copilot. Dragon Copilot is an agentic AI application that uses speech. It's some of the world's best and most widely used speech models in the world for healthcare. And it's supporting hundreds of millions of patient interactions every year. Now, the Dragon Copilot is a powerful AI companion that pulls together both Microsoft and third-party solutions to work together on a single platform to improve clinician satisfaction and improve patient outcomes. But today, we're going to show you how to build a similar application to Dragon Copilot using custom fine-tuned models that you create on Azure Machine Learning and deploy them in an AI agent in AI Foundry to bring this all together. Now, first off, what is fine-tuning? What we hear from customers consistently is that fine-tuning is extremely important to make sure that products that you're building that infuse AI is differentiated in the marketplace. Anybody can build an AI application these days that connects to base foundation models like GPT-4o or 4.1 and get some pretty great outcomes. But to differentiate those experiences based on your unique business needs, fine-tuning is a way that you can bring your proprietary data and enrich those model capabilities to tailor them to achieve the kinds of business impact that you're looking for. And in a recent survey, we found that 48% of product leaders in enterprise organizations that are incorporating generative AI into their strategies are using fine-tuning to deliver those differentiated outcomes to achieve their business goals. Now, the way that this manifests itself in applications like Dragon Copilot is they took base models, in this case GPT-4, which was the thing at the time, and they started to try to use it. And they found that it initially didn't quite have good enough outcome. And so they then took additional training data that they collected, that they had on hand, and fine-tuned it. And they still didn't quite get good enough results. So they continuously refined it based on additional data that they were collecting from their patients. And this is a common thing that we see needing to happen. Historically, with traditional machine learning models, in the early days, we called this ML ops. So this is something we're very familiar with already. You deploy a model in production, you collect data about how well it's performing, you continuously retrain it, refine it, deploy it, do A/B testing to see how well it's performing. And that's what exactly we do now with generative AI models as well. Continuously improvement using fine-tuning on data that we collected. Now, in this case for Dragon Copilot, they collected 750,000 samples of interactions with patient data. They annotated those. They continuously fine-tuned until it became one of the world's best. And so today we're going to show you how to do this sort of thing as well. Now, to get started, it's actually gotten a little bit more complicated than it was a few years ago. Because a few years ago, there were just a few base foundation models that everybody was using. OpenAI was the clear winner. But the rate of change recently has been unprecedented. I mean, there's an explosion of new models in the marketplace, pushing the efficient frontier, both on the small language model front, as well as the very large model front. And it's becoming increasingly complicated to understand which model to even start with to incorporate it in your application. Now, in AI Foundry, we bring all these models into a single marketplace, available in a consistent way, all in AI Foundry. And for many of them, we have wonderful experiences that are powered by a simplified UI, an API, an SDK to enable fine-tuning them without even writing any code, which is super, super helpful. But there's a wealth of models out there that are already pre-built and tailored to special sorts of outcomes, like processing medical image scans. And so in order to take advantage of all of those, then we also offer Azure Machine Learning as part of our AI Foundry suite to facilitate taking those models and customizing them as well. So the way we think about AI Foundry really is a collection of services all in a unified product offering that enables bringing together the tools that you already know and love, like Visual Studio Code and Copilot Studio, and enables building AI applications that infuse those AI models into your apps, enables fine-tuning them and deploying them, bringing the wealth of the collection of models that are out there in the ecosystem, the agents that you're building to enable orchestrating all of these models and plugging into your business services through APIs in your enterprise, and then our platform capabilities like Azure Machine Learning. And the Azure Machine Learning is the platform in Foundry that enables training these models, deploying them out to the cloud or the edge, fine-tuning them in code-first ways, and really having full control over the wealth of models that are out there to achieve any kind of scenario that you need to. So this is a critical part of our AI Foundry offering. And we're going to dive deep today into how to use it to achieve these specialized outcomes. So what is Azure Machine Learning? I'm sure some of you already use it extensively, but just to recap for folks, the way that I think about it is it's a platform that enables accelerating your AI outcomes. It connects to your data, your proprietary data, whether it's structured data in databases or unstructured data in data lakes, is the thing that is going to enable you to have these differentiated product offerings that you can win in the marketplace. And Azure Machine Learning has a wealth of built-in data connection mechanisms to connect to your data, automatically version the data sets for training and fine-tuning models. And you can use the tools of choice like Jupyter notebooks, Visual Studio Code, RStudio, any of the languages that you use in your companies today, you can use inside Azure Machine Learning to train and deploy these machine learning models. And then once you're ready to deploy them out to production, it has the best-in-class ML ops support with continuous collaboration across team members to work in projects, to be able to leverage built-in CI/CD capabilities to deploy versions of the models out to production using blue-green techniques to control traffic splits as you want to test new models. As we mentioned in Dragon Copilot, that is critically important because they were trying so many different versions of the models. You've got to be able to tell in production, not just in a test environment, but how well it's actually supporting your customers, achieving your goals. So having that support in Azure Machine Learning natively, super, super important. But Another key thing that Azure Machine Learning does really well and better than any of our competition is the built-in AI governance, security, and controls that enable you to deploy these models in a trustworthy, safe, and secure way. And all of that is built on top of the amazing Azure AI infrastructure with powerful GPUs, CPUs, scalable storage, and more. Now, the reasons that we hear consistently from our customers as to why they choose and love Azure Machine Learning, there's a couple of key things. First off, the accelerated time to value. The choice of tools enables you to be productive right away without necessarily needing to learn a new language. Like if you've got a legacy stack using R code, hasn't moved over to Python, for example, you can use both interchangeably in the stack, no problem. But also the ability to then collaborate across these different teams, all in Azure Machine Learning on a single project, whether it's the researchers and data scientists that are training the models, the ML engineers that are deploying the models. It's super important to be able to work together in a single platform and then be able to develop with confidence to secure, manage, and govern the application end-to-end with built-in tools for mitigating fairness, biases, and harms issues directly in the platform itself. Now, customers use Azure ML to train all kinds of models. Today, we're going to talk about how to build new cutting-edge reasoning models in Azure ML. But people use Azure ML to train all kinds of models, whether it's tiny optimized models for edge devices like inside retail stores or foundational large language models. We used Azure ML to train the Microsoft's open source family of models called 𝗲𝗲. But there's so many other use cases that customers use Azure Machine Learning for. I just want to make sure it's clear that you can, anything kind of model you want to train, you can deploy. And then you can choose to use a model directly inside of an application, or you can use it inside of an agent, which is what we're going to talk about and show today. Now, just to set baseline context, if you haven't gone to any of the other sessions this week, because we're all talking about agents right now, an agent is basically just a program that uses an LLM to control the flow of the business logic inside the application. It's a microservice with a little brain, which is a model. And just like any other microservice, it takes inputs, whether it's system messages, user messages, prompts. If you use ChatGPT, for example, those are user messages. And then it decides what to do with them. And one of the things that an agent can do with all of these different inputs is then call tools, either to search, leverage your existing proprietary data stores that you have, or to call other models, which is what we're going to show you today, is how to use the agent to then control the flow and call an external custom model that you've built and deployed using Azure Machine Learning. So with that in mind, then again, mention that we're going to use the Dragon Copilot as the example here. So in this case, we're going to show you how to build an application that helps clinicians with medical diagnoses. Now, of course, this is not something you should deploy in production. This is just a fun thing to do in the evening before dinner and the party afterwards. So please don't take the sample code and go and deploy it. But we just wanted to share some sort of an example. And in this particular case, it's a particularly interesting example, I think, because it's multimodal. We're going to show you how to use both images, and in this case, medical scans, as well as text. And so it becomes very, very interesting. And so with that, I'm going to jump into the demo here. And for those of you that haven't seen this before, this is Azure Machine Learning. In this particular case, we're in the model catalog. Now, you can see that inside Azure Machine Learning, we've got a whole bunch of different models readily available. You can actually even filter on different kinds of models based on your industry, your domain, what kinds of capabilities they support, whether they have built-in support for agentic solutions already, how you can deploy these models, whether they support fine-tuning, all sorts of things. You can filter on them, and you can find them. So there's a bunch of solutions that, like, out of the box, are kind of ready to go. But in this particular case, I know that I'm looking for a particular model, which is a state-of-the-art model called Medical Image Insight. You can see we've got this rich model cards for all of the models that are available in the catalog. And this helps you understand whether the model is fit for use prior to even spending any time playing with it. You can learn about it. Now, because this is a demo, and of course I know this is the model I was looking for, I also happen to know that it's trained on 3.7 million image medical scans across 14 different categories or types of issues. But I also know that it did not include any gastrointestinal image scans. And so what we're going to do then is we're going to fine-tune this model with additional image data that we've collected to improve the quality of the predictions, the recommendations, and the suggestions for treatment for gastrointestinal issues. So we're going to improve the capability of the base model. And this is what you do with fine-tuning in general. You take the base capability of the model and make it better with your own data. So to make that happen then, in Azure Machine Learning, one of the key ways that we share knowledge and upskill individuals across organizations is by capturing the knowledge of how to do something in a pipeline. The pipelines are reusable steps, code that are versioned. And so this particular pipeline is a fine-tuning pipeline that we've created that takes in images of the gastrointestinal issues and then enables fine-tuning the base model. And so when we run this, then what happens is it automatically distributes the code, the data, across the GPU clusters that were specified in the configuration. And we can see the exact code that's going to run. We have reference to the git commit that's automatically captured. And we can see who ran it. We can see exactly which models were emitted as a result of this run as well. So we have full lineage traceability between the input data and the output model, which is extremely important for compliance reasons, auditability reasons, and more. Additionally, we can also see in this particular case that the metrics are automatically collected as well. And of course, the curve shows that for these particular scenarios, for the gastrointestinal issues, the fine-tuned model is performing better over time as the fine-tuning pipeline ran and improved the quality of the model. So all of the metrics are captured automatically, which is great. And then I can also deploy this model directly as well. So we can just click deploy, super easy to create an online scoring endpoint. And what that does then is enables scaling the model automatically in the cloud as additional traffic comes in. So when I've deployed this model, I also get a REST endpoint automatically generated. And you can see you've got the URI as well as a scoring code that gets automatically generated as well. So you can take that code and you can integrate it into your application directly. Or you can take this URI and then you can put it into an agent. And so here in AI Foundry, then we can see I have a collection of agents already available in this project. And I can select my clinical reasoning agent. And we can see that the base model that will make the decision as to when to use the different tools that I plug in, including this custom model, is GPT-4o. I can give it some instructions, and then I can connect this clinical reasoning agent to some additional tools. And this can just follow the standard open API schema, where I provide the URI to the model that's deployed. I can also connect it to additional, whether it's logic apps or other APIs that are out there in my enterprise as well. But in this particular case, I want it to call this particular model. Now, to actually call this agent then, I built a simple application using Gradio, nothing exciting, simple Python app. Don't be impressed by it. It's not fancy. But it does call that agent, and it enables taking in the image as well as additional symptoms that are text, and provided this multimodal content, then we'll provide recommendations as to what's going on with this particular patient. So when I've deployed this particular application out to Azure, of course, and I'll go ahead and upload an image. Now, we are dealing with medical image scans. I hope none of you are queasy. We chose an image that's not particularly scary. But when I just upload an image, then it uses one of the models to process this. This is the medical image insight model that was fine-tuned now on the gastrointestinal issues. And as it goes through the image, then it identifies individual features that suggest that put some potential illnesses or symptoms. And so it's identified that it could be Barrett's esophagus or it could be esophagitis. Now, if I also then paste in additional symptoms from talking to the patient, trying to understand what's going on with them, then we can upload this as well. And the agent will then manage the session state automatically with everything that is captured from the image before, enrich it with the additional information from the patient's symptoms as well, and then correlate that and then come back with a more reasoned solution or recommendation as to what it could potentially be. In this particular case, it's recommending esophagitis, and so I've got some information here that I could then discuss with the patient. However, as a clinician, getting an answer, it's like, well, if somebody's going to ask me, why is that the answer? This isn't actually a whole lot of information. And so one of the latest crazes in AI that's really transforming the way that we can build transparency and trust is with reasoning models, because reasoning models actually go through kind of step by step and explain to you why and what to do about it and such. And so as a result, I'm going to bring Vijay on stage to actually help us take this model and expand it to build some reasoning capabilities so we can then build a better solution.
Thank you, Chris. So we just saw Chris demo how to build a model, or agent rather, using two models. And one of them that we talked about is the reasoning model. So reasoning models, many of these things, O1, O3, O4, or more recently, DeepSeek R1. So most of those things work out of the box just fine. But if you want to customize any of those things, you can do that in Azure ML. So the idea here is, if you are a large enterprise who basically has proprietary data, complex use case, and you want to use any of these reasoning models to kind of like customize them, we want to show you how to do that. So before that, let's get a little bit under the hood on what the reasoning models are. So LLMs basically started with text models, then graduated to multimodals. The text models are really good at predicting the next token. Multimodals obviously can deal with multiple images. The reasoning models, however, they basically help you with something that the LLMs do not help, which is to decompose the answer to complex problems with logical steps. That's what the reasoning models allow you to do. That way, we don't have to worry about like hallucination that you might have, or basically deducting why the answer is so. So like a math problem that you have in here as an example. So how are they different? Structurally, they're pretty much similar most of the times. Except they know how to think before they respond, which basically means it's not every question doesn't have the same time to respond. So if it's a complex problem, it'll take longer to respond because it's thinking. And obviously, you could ask, hey, I can make the LLM think by just prompting it to say, hey, think and give some reasoning before you give an answer. It's possible, but that's not like based on the reinforcement training, which the reasoning model do. So reasoning models are reinforced by training to make sure that they're always giving you the right answer and deducting the thinking behind that answer. So that's the key of reasoning models. So in that case, should I always use reasoning model? Why should I ever use non-reasoning models, right? Can I always use? Because they come at a cost. So you want to use them when you have complex use cases, when you want to have steps that are deduced, not always. But when you do need them to be like super diligent about telling you why, then that's a good time. If you can afford cost and a little bit of latency, then you can, because this is a very inferencing heavy operation. Unlike the generative models, which are just text-based. So these are, you need to think a lot more. There are a lot more tokens involved. So the latency hence is high. And you have applications that need like pretty high accuracy, like medical, pharma, law, et cetera. In that case, it probably makes sense for you to be like very, very sure and then kind of be able to kind of prove why you're doing something. So in that case, you use them. And again, when you want them to be interpretable. So that's when you use a reasoning model. So let's talk about how do you build a reasoning model, right? So reasoning model, typically, you can take a base model like the Qwen 2.5 instruct model, and then do what we call reinforcement learning, and then you can kind of build a reasoning model. But what we found is typically when you do use SFT as a supervised fine tuning as a process before, then basically it helps you converge with RFT faster, right? So we're not going to show you, we'll skip that step because Chris showed the fine tuning part of it. I'm just going to take the reasoning approach. But usually you want to do SFT and then kind of go back to doing RFT. And then that will kind of result into a reasoning model. So supervised fine tuning, you all know, you take label data and you do supervised fine tuning with it, which helps with the domain adaptation and kind of mimicking the answer formats that you want. So in this case, we are taking, let's say, MED MCQA questions, which has a bunch of multiple choice questions, and then you have an answer. So that's, you could fine tune with it. But what we did is you could take then reasoning traces from a reasoning model and feed that as part of the fine tuning data set. That basically gives the model ability to mimic a particular style of question answering. So this doesn't mean it's reasoning just yet. It's just that it's trying to comply to the answer format of thinking. And then you go add RFT on top of it. And so in terms of RFT, so what RFT involves is you have a prompt, and you take a prompt, and then you basically use a model to generate completions or samples. And then you take those samples and you score those samples according to what's right or what's more aligned or what's less aligned, and what we call computing the advantage. And then you use that advantage to score or train a model back. So typically, reinforcement fine-tuning is useful when you want better generalization, because it's going from the output, take reasoning tokens back to the output. It generalizes really well. And when you reward functions, you can have you can basically have reward functions which are more rule-based. Like you can kind of predict an accuracy and let's say the format using some simplistic rules. You could do that. And when you want to basically explore and exploit better, when you kind of go stuck with the predictive output and then some exploratory things, then you kind of look at it. And it's also more efficient because you can kind of do RFT with much lesser data than you can do with SFT. So you must have heard about two different ways of doing RFT, PPO or GRPO, which GRPO stands for Group Relative Policy Optimization, quite a bit mouthful. But let's see what it does, right? So like as we talked about in the previous example, current policy is nothing but the current model that you have in place. And then you have a sampler which takes the samples from the data set and generates completions. And these completions are then fed to a grader, which computes advantage or what we call scores for each of the samples. And then those advantage is taken and fed back to a trainer, which basically estimates KL divergence, or it basically sees how far off it is from the base model. You don't want it to be too far off. And you take that back, and then you compute loss, and then you train a model. You train a base model that you are trying to kind of make into a reasoning model. So in this case, let's take an example, the math example. And here you are basically generating samples. So you see answers sample 1 to 4. First one is right, the last one is right, but the last one does not give you the reasoning, right? So both of them are right, but you want the reasoning. So now you take these things and then you pass it to a grader, which takes these samples and assigns what we call advantage or scores, where you see one of them is rating for one of the rules that we will show in the training is rating for the answer, the other one is rating for the format. So you see the first and the last one, the answers are correct both. The format is only correct for the first one. So hence, the advantage that you get is higher for the first answers and not as much for the other answers. So you want to reinforce the model to pick the right answer and the right format together. So, and the trainer then takes and computes, calculates the loss and updates the model. In this case, the loss and the advantage is fed to the trainer, and the weights are updated to the current model. And the reference policy is nothing but the current model, which is ensuring that the trainer is not veering off too far off from what the base model is, so that it's kind of hovering in the range ways using the KL divergence. So why are we talking about, right? So you all want to do this, but training a reasoning model is expensive, right? So it's basically, it involves training, it involves inferencing, it involves multiple copies of the model. And when these models are big, they can be like pretty hard to kind of train. So you are not, so when you're doing training of a single model and you basically shard across multiple GPUs, multiple nodes, that's a complex problem by itself. You want to debug it, you want to basically profile it, that's hard. Now you add to it the sampling approach, the grading, where your grading can again be code or model. So at any given time, you could have multiple copies of the model running on your platform, potentially distributed. So it's an intensive process, right? So you need the right platform support to be able to do that. So as we talked about, we have multiple components: the sampler, the grader, the trainer. So they all communicate, and they kind of for inferencing. So you got to be able to debug them, log them, profile them, look at the metrics, do all of those things. Similarly, compute heavy. You want to make sure that the models are kind of multiple copies of them. They're efficient for inferencing and training and scaling and data loading. And that's where Azure ML comes in handy. And I will show you the demo of how to kind of do this on Azure ML. And the way we do that is, like, obviously at the bottom layer, we have some access to all the GPUs of highest class. You can run jobs that goes across thousands of GPUs because they're networked using high bandwidth InfiniBand. You can have optimal storage options like blob or Lustre, and then you have compute options like managed AKS or unmanaged AKS, and so on and so forth. And you have all the key frameworks built in. So basically, be it MS-SQL, Onyx, or DeepSpeed, which we'll talk about some of it, Nebula checkpoints, so you can checkpoint your data weights and then kind of reload them. And you have your Azure container for PyTorch, where all of them are prepackaged, so they're like, you don't have to kind of do it. So these are complex things, so we want to make it easy for you to kind of just pick up and go on the fly. And then you want to do your job management, you want to look at your node health, your environment management, experiment tracking, data mounting, et cetera. And obviously, once you're running, you want observability, right? You want to do interactively, log in, SSH, debug, you want to do all of that. You want to have metrics logged into App Insights, a run history, and we have all the logs. You want to look through the logs. Logs can be very, very wide and intense. You want to look at that. You want to be able to profile so that you know where it is, and the infrastructure metrics as well, and then you go from there. With that, let's jump into demo. All right. So right here in Azure ML, again, plug for Azure ML, you can basically have your notebook. You can basically do everything right here. So we'll walk through how do you set up for a given job, the AML resources, and then how do you train a reasoning model using AML, and then launching the job and looking at the results, like debugging, monitoring, and all of those things. So first step, we look at basically setting up all the required packages and CLI tools to get started, like Azure Core, the Python SDK, Azure CLI, and so on and so forth. Let's execute that. And while that's running, we look at the fact that we want to now first download the instruct model, in this case, 𝗀𝗀𝗀𝗀𝗀 2.57b instruct model from Hugging Face. So you take the Hugging Face token and you download it. You do it once, because once you do it, you basically have the model in your workspace, and the workspace then manages the model copy for you. Then you can use it again and again. So you got that. And then we basically, the setup process, you want to set up your data set that you want to use, the model that you want to use, the compute cluster that you want to set up, H100, A100s, any of those things. In this case, we'll use H100s and we'll use 2 nodes. And environment setup, like we talked about the things that are set up out of the box. And then in this case, like the TRL library for the GRPO trainer that we talked about, that will be set up as well. And then LoRa for parameter efficient fine tuning. With that, you basically get that set up. Now, let's look at the data set like we talked about, right? So the data set is you have like bunch of the questions, bunch of options, and then we want to basically have thinking tokens in here along with the answer and the final answer itself. So this is a data set that we have that we want to kind of reinforce the model with. So when we looking at the GRPO trainer, like we talked about GRPO trainers, it has 4 steps: generate completions, estimate advantage, or compute advantage, estimate KL divergence, and compute loss. We will see all of that running. And so you have the samplers, you have the reward functions, you have the trainer, all of those things. So we'll set up all of those. And Azure ML makes it natively easy for all of those things. So for example, I talked about inferencing. So inferencing, you want to do inferencing of the samples itself. So you want to generate a lot of in the same training cluster. So VLLM is a very inference efficient engine. So we want to have that integrated. And then you want to use deep speed to kind of do distributed training. So we'll kind of talk about that. And LoRa obviously helps you to do parameter efficient fine tuning. And then obviously tracking, debugging, and metrics. We'll go over that. So GRPO, so all of that is GRPO encapsulates basically your base model and reward function, and your sampler, trainer, and grader in the function itself. But in terms of how you set it up, you basically set up the current policy, which is the model. That's in this case a Qwen 2.57b model, and then the reward functions that you want to use. We'll quickly walk through the reward functions as well, and then the data set that we just went into. So you set it up. And the reward functions, what does the reward functions look like, right? So reward functions are like, so here you want to say, hey, the pattern that you want to have in every answer, you want to have a regex, which basically says, hey, I have a think tokens before it has a answers answer tokens that you have. So you want to specify that. And then you want to basically in the config specifically have you want to like how the VLLM is run. So VLLM, the inferencing engine, you can run it in a server mode where you have separate nodes running the inferencing itself. You can do that if you have like large workload, you have enough compute, you can do that. But in this case, because we are like trying to do that in just 2 nodes, we'll do it in the collocate mode. So we'll kind of have it in a more efficient manner. So we use collocate as the ability to run the inferencing engines. And then you have your reward functions that you define one for accuracy, one for format. Right, and then you define the weights that you want to use. You want to use weight for accuracy, differently for your format. Sorry for the pop-ups. And the metrics are being logged in Azure ML as well. And then let's say the deep speed config that you have. So we talked about deep speed. Again, it's optimization engine that allows you to do distributed training. And you basically have multiple stages in it, or multiple modes of operating, stage 0, 1, 2, and 3. Basically, all of these things determine, I should have turned off the notifications before, sorry. So like in stage 3, what you have is you have all your the optimization states, and then you have your models, and all you have your gradients sharded across different GPUs, right? So that way it's memory efficient because the model is large, the data potential is large, and you want to use that so it can scale horizontally as you add more GPUs and more nodes. Similarly, you also want to then further optimize by saying that, hey, you want to offload your optimizer computations to CPUs so that your GPU memory is freed up and you can kind of be more GPU efficient. I mean, and it'll be very handy to have more GPU memories. We talked about the stage 3 and then batch size, etc. that you want to set up. So you can basically set up all of this in Azure ML. So finally, let's basically let's set up the job itself. So which has the config file we talked about, the trainer.py file, and then the command itself that you have in here, where you talk about the instances that you're using that is distributed, and it's a use PyTorch library to kind of train, and you have your environment variable set up so that you can use your profilers, which will be very handy, which we'll see pretty quickly, etc. out of the box. And then finally, we submit the job. And this job can potentially take, so we just saw the job that we just kicked off. You see a link to this. This job can take a long time. So I have some jobs that I have run. So we'll go to that, and then we'll see quickly. But while we finish, I'll tell you the next steps as well, which is about registering the models and then tuning. But let's see if we can go back and see some of the existing jobs. So these are the jobs that I've been running for the last, and they take about, they all, if you can see, they're all running on H100, 2 nodes. So we can take one of these jobs to previously that it ran. So this is a job that ran. So like, let's say we look at metrics. So metrics, so now in reasoning models, the metrics that you have are different than the reasoning metrics that you have for the rest of the training. So reasoning model, for example, when you're doing, you want to see, like, optimize for how long your completions are. So you, for example, your completion max length, and average length, you want to basically check to make sure that the answers that you are generating are of sufficient, whatever is appropriate for your domain. You want to make sure that they're good. Similarly, you want to have more metrics. So you have them here. So let's say you have your reward functions. Like similarly, if you want to optimize for your rewards itself, that we talked about computing the advantage or the scores. So you can kind of get all of those things. Similarly, if you want to debug any failed jobs, if your jobs were to fail, obviously, as you can see here, you can go and look at logs. You always have the choice. But the logs can be overwhelming, especially as you scale. As you scale, you will have too many logs, too many GPUs, too many nodes, all of those things. You could do that, or you could use what we built for you, which is maybe I can go back here as well, and then so there's a for example, here the job logs link, where you can go look at the logs link, and it takes you to your profiler. And then if you run this, which I did just now before the demo, you can actually see that if you had like any errors, in this case, like out of memory exception, you can catch it right here. So you don't have to go, even though it's distributed, it works as though it's like local one node that experience, because it's like scouring all logs that you have across all GPUs, all nodes, and then you just can quickly, just simple queries, then get to things that you're looking at. Similarly, if you have, let's say, any of the jobs, if you want to look at profiler, I should have not clicked on it because it might take a little longer. So yeah, so this is basically the job that ran. You can literally profile this data. You can see what's going on in here. Like you can see that we are using VLLM. So you can kind of basically profile your large jobs across GPUs and everything else pretty handy. So that way, you have all the tools that you need to kind of manage your jobs, like the issues that we talked about that the reasoning models are required to do. Once you have that, you come back, you register your model just like you do with any other model. You deploy the model for inferencing, yeah, you can just debug the trace, etc. So that's how you train a reasoning model. So just to quickly recap, so as the models get better, you want the ability to kind of like, let's say, you want the freedom to go to Foundry, get the model that you want, but you want to be able to say, hey, we have data scientists who can basically customize it for my data. If so, Azure ML is there for you guys to do it. So I'll invite Chris back on stage to come back and do the remainder of the session.
Right. Thank you, Vijay. All right. So I'm going to show now, side by side, now that we have the reasoning model, how do they actually perform compared to the original model? Remember, in this application, we simply submitted the images. We'll do that again. And the base model will certainly interpret this in a certain way. And of course, these models are non-deterministic. We've all used these types of models and seen this behavior in the past. But we can see that the model that doesn't use reasoning, it gives us an answer of potential symptoms, potential issues that we need to talk about with the patient. But the answer from the reasoning model feels a little bit more comprehensive. I can kind of understand a little bit more what's potentially going on here. And then if we provide the symptoms again, in addition to the image, then again, it just feels like I'm working with an actual partner a little bit more. I've got a lot more details. It's, again, non-deterministic, so not as helpful of a response as I would have hoped for. But it's optimizing for length and now if I ask for a recommended treatment, and then I can go through and use my own expert opinion and make some decision as to how to proceed with the client. Now, ultimately, you're going to probably not build these types of models. Most of you, some of you maybe are in the medical domain. But the steps that we described to go through and actually train a custom model using Azure Machine Learning, deploy it out to the cloud or the edge, and then incorporate it in an agent is something you can absolutely do and follow along at home. If you download the slide deck after the fact, Vijay and I's LinkedIn information is available on the first slide. You can always reach out to us for questions, certainly. But the couple of things that I want to make sure that you take away from this session, first, certainly how to use Azure Machine Learning to fine-tune and deploy the models, embed them in agents, and be able to use Azure ML at scale, training on models on thousands of GPUs. If you haven't used Azure ML already and used Foundry generally, please definitely join one of our many customers out there. Give it a try. There's no reason not to. And we've got a couple of resources here that make it easy to get started. As I mentioned, there's a lot of sample applications, default agent templates, models in the catalog to get started from. So it makes it really, really easy to get started today. So thank you all. Really appreciate you joining us. We've got a QR code here for recommendations as to what else to dive into. Certainly, As we know, the party's about to start, the conference is almost over, but you can get all this content online after the fact as well. It's all been recorded, and there are a lot of other sessions, both on AI, agents, and a whole lot more. So please dig in. Thank you again so much for your time. You've been a pleasure. Appreciate it.